Hello students. So with our last class we have come across, or else you all are aware with the file system interface there. Okay, so wherein we have come across to know regarding what do you mean by a file system, or else what do you mean by a file system structure there. We have come across with directory structure, disk structure. Okay, then what are the different SS methods involved with respect to a file structure. Okay, so then followed out you all are aware with what are the different protection schemes with respect to your file system. Now let us come across with and one more small section which is a part of your module 4, and that is file system implementation there. How an implementation takes place with respect to any respective file system there. Okay, so when we are proceeding towards this implementation, so these are the things which you will be studying in detail here. Okay, so what are those? Firstly, all of you are aware with a structure. Okay, so little bit and extended version you guys are studying here in file system structure. Then you are coming across with implementation, directory implementation, allocation methods, free space management. Okay, so this is the layered file system. That is how, or else what are the different levels in which and file system behaves there. One is there is a file system being managed at the application program level. Then at we have logical file system, file organization module is the basic file system, then input output control, then towards the devices. Okay, so the journey goes from application programs till the hardware devices. Okay, so through your input output controls. Okay, else it can be basic file systems there and all these things. So with respect to the file system implementation, there are two things what you should know. One is called out as boot control block, and one more is called out as volume control block. Okay, so what are these? So always keep in mind there are several APIs. Okay, I have kept on telling you we have different system calls at the API level. Okay, which will tell us how this implementation of these functions takes place there. Okay, so on disk or else in memory structures there. Boot control block is nothing but it contains the information needed by system to boot operating system from that volume. Okay, so that is needed if volume contains operating system, usually first block of the volume there. Okay, one more is volume control block I have. I call this as a super block, or else you call this one as a master file table, which contains all the volume details about a respective file. That is, what is the total number of blocks, what are the number of free blocks on it, what's the block size, free block pointers or array. Okay, these all things are held in this volume control block. So that's why we call it as a master file table there. Next, directory structure is a one which organizes these files. Okay, every directory structure has file names with it, inode numbers, and a master file table there. Okay, so then let us come across with a detailed view towards this FCB. That is, every file does have this file control block there. What is this file control block? Regarding a file, the information is stored, and that storage of an information is called out as file control block. Okay, it has the terms like, for example, it has file permissions there. Okay, so then we have dates of it, who is the creator of it, who is the group owners. Okay, then what's the file size, file data blocks or pointers to the file of the data blocks. Okay, so these all things are held with respect to any FCP there. Okay, you can just come across. It is with INO number, permissions, size, date. Okay, all of them are being stored in master file table using relational DB structures there. Okay, NFTS is nothing but network file transfer system there. Okay, so these are the things which it holds in all. Okay, in memory file system structure. Okay, so you have certain things there. Okay, so what are those? In memory, what happens now? Okay, in memory is it has to mount the table and unmount this particular master file table there. Okay, this mounting and unmounting is been referred in our further slides with an block diagram, so you can get across to know. Okay, so mounting is nothing but getting the file to the physical memory. Okay, and then unmounting is nothing but closing that particular file. Okay, so it open returns a file handle for the subsequent use. Data from read eventually copied to specified user process memory address there. You can just see that this is for open and this is for read. Okay, so whenever for us it is just opening up of a file, but what happens when you open, you just open it along with the file name. This is the API. Okay, the full API is not been demonstrated here, only just for your reference, it's just open. Okay, so what happens through this API, it it sends the control towards the kernel memory, okay, saying out that this particular file has to be opened. So now what directory structure does is it refers that particular file name. Okay, that file name has been identified by the inode number as I spoke to you. Okay, it is been referred in the respective directory structure. Okay, that is held in the secondary storage. From the directory structure, it might have a single file or else it can have multiple files there. It refers that file back to the directory structure, and that file is been controlled, or else that file is been opened. Okay, so that is through this particular blocking structure, that is along with the permissions, what is the size of it and other things there. Okay, what happens when it is with read? Okay, you are reading a particular file there, so at that time every file has an per process open file table there. Okay, what will that have is it will have an index. What is that index doing? It is pointing towards the system wide open file table there. Okay, this points towards the data block. Okay, from where these particular data blocks have been referring this file control block there. Okay, file control block is being referred, and through that it will come to note that which data blocks are being asked there, and those data blocks are being read for that particular file. Then comes is partitions and mounting. Okay, so what do you mean by partition now? Partition can be volume containing a file system. Okay, so that is when you are when you are doing any kind of a booting that. Okay, boot up the volume or it's a loader. So we have many multiple set of blocks. Okay, so what do? I root the partition contains the operating system. Other partitions can hold OSs or else other file systems. Okay, so it can be mounted at the boot time. Other partition can mount automatically or manually. At the mount time, file system consistency is being checked. Is all metadata correct? Okay, if not, fix it, try again. If yes, add to mount table, allow the SS. Okay, next term is called out as virtual file system. What do you mean by this virtual file system? It's on the UNIX, okay, which provides an object-oriented way of implementing file system there. VFS allows the same system call interface, that's the API, to be used for different types of file systems. It separates for file system generic operation from implementation details. Implementation can be done, can be one of the many file system types or network file system there. It implements vnodes, which holds inodes or network file details there. Then dispatches operation to appropriate file system implementation routines there. Okay, so it refers to vnodes here. As we have inodes, okay, so in the same way we have vnodes with respect to virtual file system there. So this is the one wherein it separates file system generic operation from implementation details there. Okay, then it is this virtual file system now. Okay, the API is to VFS interface rather than any specific type of file system. I have my file system interface, I have VFS interface. What will this do is it will refer individual local file systems which can be on the same disk or else it can be remotely held in some other respective system also. Okay, then how is my directory being implemented? Okay, so a directory implementation goes according to the linear list of the file names. Okay, linear list of file names with pointers of the with pointer to the data blocks. That is, it is simple to program. Okay, time consuming to execute. Okay, so wherein I use across with the linear search time. Okay, so for implementation, it can be any different way of finding it. Okay, so you can use linear search time for it, or else you can even use your B plus tree. Okay, so need not worry. Yeah, B plus tree you guys have come across with your data structure then, but in detail in your further semesters, you are coming across with file structure as one whole subject. Okay, so that time you'll be coming across in more detail with this B plus tree there. Then either you are using a linear list or else you use a hash table. Okay, now what's this hash table? Hash table is linear list with a hash data structure. Okay, it decreases the directory search time there. Okay, so wherein we are expecting collisions. So what are these collisions? Situations where two file names hash to the same location there. So at that time, that management has to be done. So that is called as collision. Okay, only if entries are of fixed sign or else fixed size, or you are using a chain overflow method, then this happens to be an used one. Then let us come across to know what there are different allocation methods now. What are these allocation methods? How is the storage happening across in the memory, in the secondary storage? That can be in terms of contiguous, or else, as we have come across, it can be uncontiguous also. Okay, what do you mean by contiguous? What do you mean by allocation? An allocation method refers to how disk blocks are allocated for the files. Okay, one is contiguous allocation. What do you mean by contiguous? One after the another. Each file occupies set of contiguous blocks. It says that I want these three blocks. That's all. Okay, it's best performance in most of the cases. Okay, but and it's even simple also. Okay, wherein you have your starting location, you're known with the length, and you can straight away fix out that these are my contiguous allocations which can happen. Okay, the problems what are included with this contiguous allocations are, you should know the space for the file, you should know the file size. Okay, it can involve in some cases external fragmentation. Okay, need for compaction offline, that's a downtime, or else online. Okay, then you can just come across with this example here. Okay, mapping from logical to physical memory. Whenever you are doing it, assume this is my secondary storage, this is my directory structure, these are all my different file types now. Count is my file type, which it says it starts with 0, length is 2. So starts with 0, length is 2. TR is my another file which starts at 14 and length is 3. It has start with 14 and length is 3. 14, 15, 16. These three are allotted. Male is 19, okay, and whereas the length is 6. Similarly, 1, 2, 3, 4, 5, 6. Similarly, the other ones. Okay, but what is one of the drawback here is there are many what do you say, unvisited blocks over here. Okay, but sometimes, when of course they will be used in some of the other cases, but it is known, but it has to be known that these things are free. Okay, and it will be not with the fixed sizes. Now assume you are at my file is something with some file name called as f1. Okay, and it is starting across with 2. Okay, and it has to end with 4 only. Okay, 4 as my length, it cannot have 5 as my end of the block. So sometimes we feel that of course we should know the size of the length of the particular storage only, then this happens to be a used one. Okay, block to be assessed is q plus the starting address. Displacement into block is given by r, that is the length there. Okay, so there is one more called it as extent based systems there. Okay, so many newer systems, we call them as vertias file system. Okay, use a modified contiguous allocation scheme there. What is this? It's an extent based file system, okay, which allocate disk blocks in extents there. And extent is a continuous block of disks there. That is, extents are allocated for file allocation. A file consists of one or more extents there. Okay, let us come across with one more allocation method called as linked allocation. Okay, this was one. Okay, contiguous. One more was linked. What is this linked? You all are aware within your data structure with linked list there. The same thing follows here also. Okay, here it says that each file is a linked list of blocks. File ends at a nil pointer. No external fragmentation arises here. Each block contains pointer to the next block. No compaction, that's no external fragmentation. Free space management system called when a new block is needed. It improves the efficiency by clustering the blocks into groups, but increases internal fragmentation to an extent. Okay, reliability can be a problem. Okay, locating a block can take many input, output, and disk seeks there. Okay, there is one more called as file allocation table. Okay, which varies, or its variation is with beginning of volume has table indexed by the block number. Okay, then it is much like the linked list but faster on disk and catchable. New block allocation is quite simple here. We can just come across with linked allocation is each file is a linked list. Okay, now block is equals to pointer, then it has the information. Okay, blocks may be scattered anywhere on that particular disk. Mapping here goes across as qth block in the linked chain of block representing the file. Okay, whereas displacement into block is r plus 1. Okay, I have with an incremental value there. Okay, until where it has been allocated, then plus 1 to it. Okay, this is linked allocation now. This is my file name called as Jeep. It starts at 9, it ends at 25. Okay, this much I know it. So it starts at 9. Okay, you can just see that there is no contiguous allocations here. From 9, it has been allocated with 16th block. From 16, it is allocated with first block. Then from first it is being allocated to second. Okay, and from second it is being allocated to 25. Okay, so you can just see that there is an of course the size of this is 4 blocks here. Okay, but I do not have it in contiguous way, I have it in a linked list format then. So this happens to be wherein you will be overcoming that external fragmentation. So this is one file allocation table. As I said, it is quite similar to your linked list there. You can just see that this is the name. Okay, this is my start block. Okay, it says me that this is my file allocation table. At 217, it will be having the address pointing towards the next respective uh, content there. Okay, it is pointing towards to 618. It refers 618 here. 618 says 339. These are all addresses there. Okay, ultimately these are the 3 blocks which are used for storing a particular file entry called out as test. Okay, then comes is your allocation methods, that is indexed way. Okay, each file has its own indexed block now. Okay, index block of pointers. Okay, so logical view is I have my entries here, and along with that I have the indexes to where it is referring. You can just come across here. It says my file name is Jeep, my index block is 19 now. At this 19, okay, I have indexes to which it has been referring. Okay, at 19, it is referring the index called out as 9. Okay, it is referring the index called out as 16. It is referring 1. Okay, it is referring 10. It is referring 25. Okay, it is referring 25. Then I have across with -1. So -1 says ultimately it's the nil. It's pointing towards the null pointers there. Okay, this is the end now. Okay, so this is an just an extended version towards your linked list itself, but I have an indexed version to every allocation there. Okay. So it says that it needs an index table. Random access is possible here. Dynamic access without external fragmentation, as I said you, but have overhead of index block. Okay, mapping from logical to physical in a file of maximum size of 256K bytes. Okay, and the block size is 512 bytes. We need only one block for index table. Okay, Q represents your displacement into index table, whereas R represents your displacement into the block here. Okay, so with the same one, okay, with your indexed allocation mapping there, okay, you can just come across wherein it says mapping from logical to physical in a file of unbounded length, where I have more than 512 bytes. Okay, linked scheme works here. Okay, whereas no limit on the particular size. Okay, wherein it says Q1 R1, Q2 R2, it is with 512 by 512, where I have an huge flow of it. Okay, so it is with Q1 is block of index table, R1 is used as follows. Again, R1 refers with Q2 and R2. Q2 is displacement into block of the index table, whereas R2 is displacement into block of file. Okay, similarly, you can just go across with the next respective example for the same. Okay, if I say 2-level index, so 2-level index says that it is with R1. Okay, then R1 refers with R2. Okay, so this is my outer index. Okay, outer index is in our case it happens to be Q1. Okay, so this happens to be a index table which is being allocated with the references there. Okay, it can be with R1 and R2. So this is one example of your UNIX file system then. Okay, that is UFS. It says 4K bytes per block, 32-bit addresses have been stored here. You can just see here, these are my direct blocks here. All of them are being referred with data blocks there. Okay, there's a single direct data block. This is double direct block. Okay, single says that one reference it has, and those are being referred with the next data which it has. Double indirect says that one has an index towards two other index files, and those are being referred with the data files. Okay, so these all happens when your block size starts increasing there. Okay, then the last one is your free space management. Okay, file system maintains free space list. Okay, as I have a bit vector or a bit map there of n blocks. Okay, if I say if I take an array of bit of I, okay, so I just say that wherever I have an 1, it is nothing but it's free. Okay, wherever I have 0, I say that that particular block of I is occupied. Okay, Block number calculation, how is that been done is number of bits per word into number of zero value words plus offset of first bit. Okay, CPUs have instructions to return offset within word of first bit. Okay, let's come across here. Bitmap requires extra space. That is example, now like for example, block size I have 4 KB. That's equals to 2 raised to 12 bytes there. Disk size I have 1 TB. That is 2 raised to 40 bytes. Okay. So now comes is with how to find this my n value now. Okay, how to find this n number of blocks. N can be 2 raised to 40 divided by 2 raised to 12. That's equals to 2 raised to 28 bytes. Or else I can call it as 32 MB. If 32 MB I have, okay, I can divide it into 4 blocks now. Okay, 4 blocks. Each block can be of 8 MB of memory. Easy to get contiguous files there. Okay, so this is with the linked free space list on the disk. Okay, you can just see that linked list, free list now. Cannot get contiguous space easily here. Okay, no waste of space. No need to traverse the entire list. Free space list heads. Okay, you can just find that these are free spaces now. 2, 3, 4, 5, 8, 9. Okay, these are all free spaces which can be got to know through your linked free space list on the disk there. Okay, for this free space management, okay, you have three different ways of managing it. One is called it as grouping. What do you mean by grouping now? Modify the linked list to store address of next n minus 1 free blocks in the first free block, plus a pointer to the next block that contains a free block, so that you can get to know like this. You can get to know how many number of free blocks can you get. One more way is you can have counting there. Okay, because space is frequently contiguous, used and freed. Okay, with contiguous allocation, okay, it extends or clustering can happen there. Keep the address of the first free block and count of following free blocks there. Go on, have a count header there, and go on increasing. We can go on increasing across with the count value. Okay, so through this you can get to know what's a free space. Okay, how much free space is available. Free space list then has entries containing addresses and its respective counts. One more is you can have space maps there. By using space maps, you can consider metadata input output on very large file systems there. Full data structures like bitmaps, okay, could fit it in memory. Thousands of input outputs are there. Okay, it divides the device space into meta slabs units or manages meta slabs. Okay, that is given volume can contain hundreds of meta slabs. Each meta slab has associated space maps there using counting algorithm, but records to log file rather than to file system there. Log of all the block activity in time order in counting format. Metaslab activity is almost like load space map into memory in balanced tree structure indexed by offset. Replay log into that particular structure, combine contiguous free blocks into a single entry. This is what happens in your free space management. Okay, I hope so everyone has got to know it. Okay, this completes your module 4 with your file system structure and file system implementation. Thank you.